All right, I'll turn it over to you, Anders, for the introduction. Thanks so much.
Thanks, John, and welcome everyone this afternoon. Glad to have another Geospatial Forum presentation from a speaker here at NC State. Today we have Dr. Peter Ojiambo, who was born and raised in Kenya, earned his BSc and MS at the University of Nairobi, and later a PhD at the University of Georgia. He joined the faculty in the Department of Entomology and Plant Pathology here at NC State in 2008. Now he has become a full professor and university faculty scholar, which is a major accomplishment. His research program at NC State focuses in on theoretical and applied epidemiology of plant diseases and pathogen population dynamics. Today, Peter will be highlighting his research focused on long-distance spread of plant diseases using Cucurbit Downy mildew as a model system, which is an important disease through much of the southeastern part of the US. So please welcome Peter. We plan to hold verbal questions until the conclusion of the talk, but feel free to enter any questions that you have into the chat as we go. So Peter, take it away.
Okay, Anders, thank you so much. And good afternoon, everyone. So this afternoon, I'm just going to be talking to you guys about some of my work that I've done over the years on Downy mildew. I've been very deliberate in selecting certain aspects of this particular work just to highlight what I've done and sort of make it relevant to the audience that is going to be listening this afternoon. And so, okay, let's see, good. So just a little bit of information background about Downy mildew. Downy mildew is caused by an oomycete called Pseudoperonospora cubensis. The disease actually has a global distribution and occurs pretty much wherever cucurbits are grown. And you can actually see the pathogen. This is called a sporangium of the pathogen that is actually responsible for infection, and it can actually be dispersed over long distance. And so warm and humid weather, is conducive for the disease. And if you look at the symptoms on the crop, they're quite varied depending on the host that is actually infected. And the pathogen infects a wide range of cucurbits, including cantaloupe, cucumber, and squash. And so you have to be, in terms of the symptomatology, you just have to be well versed on how it looks like. Otherwise, you can actually miss it. For example, squash looks like there was fire in there in the field, but on cucumber, it's very, very nice. Chlorotic lesions on cantaloupe as well. So what's the status for the disease in the United States? So it's primarily a major problem in the eastern part of the country because that's where the conditions are conducive for the disease. And in 2004, there was a resurgence of the disease primarily on cucumber. And a lot of this had to do with an introduction of a new strain of the pathogen that was able to overcome resistance that had been very, very effective for the last 40 years since 2004. And since 2004, the disease was a major problem in California. And growers have to pretty much, they expect to see the disease every year. And because of that, they are very diligent in terms of disease control. So as far as control options are concerned, they're very, very limited because we don't have a lot of resistant cultivars. And there's a reliance on fungicides, for disease control. And these fungicides need to be applied on a particular time because the disease spreads very, very fast. The timing of the initial spreads are very, very important. And so in that regard, prediction and disease forecasting is actually very, very important for this particular pathosystem. So if you look at the seasonal spread of the disease in the United States, for those of you that are familiar with the pathogen, the pathogen is actually an obligate parasite. In other words, it cannot live without its host. And so during the winter, for example, the pathogen cannot survive above the 30th latitude. Sorry. It cannot survive above the 30th latitude because the conditions are very severe there. There's no crop out in the field. Everything's going to be killed because of the winters. And so it only overwinters below the 30th latitude in southern Florida where we have a kind of like subtropical kind of climate that allows for year-round production of cucurbits. And so we have a monitoring system in place, that have been put in place primarily during the resurgence of the disease to be able to monitor and report, new outbreaks of the disease. And this reporting system has been very fundamental in sort of generating data that we have used over the years to better understand, kind of the epidemiology of the disease, the temporal and spatial components of it, and how the risk of the pathogen emergence in some of these upper states occur during the growing season. And so I'm going to talk about three important items. I just want to emphasize, I've been very selective to show what I need to show for this particular audience. Most of this is a mix of very old stuff that I've done over the years and much more recent work. And this has been targeted specifically just to look at the things that are useful in terms of dynamics in time and space, which the geospatial center is all about. So the first thing that I'm going to be talking about, just to look at the dynamics of the disease spread, looking at this temporal and spatial spread, look at some of the risk windows that have been identified in terms of disease spread in time and space. And the second part I'm going to be talking about this afternoon is to look at risk, the risk of disease outbreak at the landscape level, primarily looking at some of the work we have done in terms of modeling and sort of identifying the patterns of the disease spread, and also looking at some of the stability of the spread parameters when you are looking at the epidemic spread in time as well as space. I'm going to talk a little bit about that later on in my talk. And the last component is a little bit more recent work, on network analysis, where I had a student with Dr. Alan Lloyd in the math department, who was conducting some network analysis stuff, primarily to identify highly connected sites that we could target in terms of disease control. And I'm going to explain a little bit later on why that is the case. So look at the first objective, just looking at the temporal dynamics in time and space. As I've said before, most of the data set that I've used over the years has come up from the disease monitoring network. It's just an example of an epidemic map. This was for 2009 that reports on the disease outbreak, how long ago outbreaks have been reported and in which particular site. So this is an automated system where we allow our collaborators, whenever they have a positive ID of CDM, they go to the website, they report it, and the map automatically populates. So we have been doing this since 2008, and most of the things that I'm going to be talking about is for data generated during that particular period of time. So as far as the dynamics is concerned, some of the three things that I'm going to be talking about today is, what's the temporal spread of the pathogen, of the disease within the country, what the special extent of the disease, and then what are some of the risk windows in time, in space and time, during which the pathogen and the disease is actually a major problem. So if you look at the temporal aspects, this table basically summarizes some of the observations of the disease, collected in 2008 and 2009. And we have, states in red are the ones that in the southern part of the country, and the ones in blue are the ones that are classified a little bit, in the northern part of the country. So we have the number of cases, and we have the epidemic duration. And then on the last two columns, just gives you the idea of the rate of spread in terms of the new cases per day. So you can actually see from this, the ones in the southern part, the rate of spread, the number of cases per day is very, very small compared to the ones in the southern part, the northern part of the country. And a lot of that has to do with the fact that the epidemic duration is actually much shorter in the northern part compared to the southern part. And that's not unexpected, because the pathogen starts from southern Florida and it goes up. And during the winter, everything starts slowing down in the fall and coming back. So you have the states in the northern part have a very short window during which infection can come. But if you look at across all the 24 states, based on the epidemic duration and the total number of cases that we collected in those 2 years, the rate of, we have about 1 to 2 new outbreaks occurring per day. So when the disease starts, this information can just help us determine how fast the epidemic is likely to occur over a certain number of days or over the growing season. And this is part of the information that we did not know before, and just added some new information to help us better understand how fast the disease moves in different, during the growing season, and taking into consideration differences in terms of the environment, the host, and of course the inoculum availability. So what about the rate of spatial spread in terms of distance? At the same time, again, we used here the maximum distance between two cases that are far apart in a particular year to be able to look at the distance over which the epidemic and the disease could actually move. And then we looked at the epidemic duration during that particular period of time. And the spatial spread was simply expressed as the maximum distance divided by the epidemic duration in that particular year. For example, in 2008, the maximum distance was between a report that was reported in Florida and one that was reported in a county in the Columbia County in Wisconsin. Okay, and you'll notice here in both years we always start from Florida because that's where the overwintering takes place. So based on that, we could actually tell that one would expect that the spatial spread of the disease is about 9 to 10 kilometers per day. And you can do the math a little bit to see how fast that epidemic really moves during the growing season. So how do these numbers compare to other long distance dispersed pathogens? Our numbers for Downy mildew are very comparable to those of tobacco blue mold caused by Pseudoperonospora tupacina, where the spatial spread is about 8 to 9 kilometers. But our numbers for Downy mildew are much, much lower than ones for soybean rust, for example, which is about 18 kilometers per day, and the one on stem rust on wheat, which is up to 76 kilometers per day. So you can see there's a little bit of differences in terms of spread, on a spatial scale. And a lot of this has to do with the ability of the pathogen to survive during transport. And if you look, for example, Downy mildew, they're highline, they cannot survive long in the atmosphere compared to rust, for example, or spores that are very, they are melanized and they can survive the UV radiation during transport. And that allows them to move over a longer distance compared to the ones of Downy mildew. All right, so one thing that also I did was to sort of look at, okay, what are some of the, we know we have a special numbers in terms of spread, but we wanted to sort of use a different approach to be able to see whether we can still get the same level in terms of spread. So we wanted to develop an alternative approach to be able to determine if indeed the values that we are seeing in terms of spatial spread are very, very consistent. So to be able to do this, we went back to the data set and sort of plotted on the x-axis here, we have the day of the year, and then on the y-axis you have the latitude, and the symbols in red is the date of planting, the symbols in blue are the ones where the first disease occurrence actually reported. So these are plotted based on the day of the year and the corresponding position that we had in terms of the latitude. So we thought we could actually use this information to better determine the spread of the pathogen on a spatial scale and help us also better compare how these observations look like when you're just using the maximum distance and the number of cases that are reported. So if you take the gradient of this particular line, for example, in 2009, for the one for the disease, first disease occurrence, the gradient was about 11 kilometers. For the one for 2009, which is actually here, the gradient was about 13 kilometers. And you'll notice here that the gradient for the planting occurs first before you see the disease. So there's a correspondence between planting, and then of course you have to wait for the crop to mature, and then of course after that, and you have infection taking place. So if you look at these numbers are very comparable to the ones that we obtained using the maximum linear distance, which was 9.2 and then 10.5. So this gave us quite a lot of confidence that at least the numbers that we're coming up with the spatial spread are very comparable and they're actually consistent using different approaches. So in summary, able to actually show that the rate of spatial spread of Downy mildew is about 10 to about 13 kilometers per day. All right, so one of the things that we wanted also to figure out in terms of spread and epidemiology, we know the inoculum is very, very important in terms of spread of the pathogen. And so one of the things I wanted to figure out, okay, how far does the inoculum move? Should we worry about, for example, if you have a field that's infected here in North Carolina, should somebody, for example, in Pennsylvania or New York, worry about what is being produced there and whether the disease is not being controlled? So to be able to address this particular problem on how far the inoculum moves, we actually utilized what we call the point pattern analysis, basically looking at the occurrence of the observations in time and space, and try to figure out how they are actually correlated, or somehow if they have a pattern in a particular space in time. And so we use the O-ring statistic here, which is actually given by this particular equation here, where lambda here is actually the intensity of the spatial process. G is actually the correlation, the pair correlation function. And we know that when the statistic is actually greater than lambda, you have an aggregated pattern. And if it's less than lambda, you have an uniform pattern. So this was a very good starting point to be able to show to what extent the inoculum can actually move based on the disease observation that we have. So we did this for both 2008 and 2009. I'm just going to explain this a little bit. So for example, here on the x-axis, here you have the spatial scale, this is the distance. On the y-axis here, you have the statistic itself. There's a faint gray line here, which is actually the lambda itself, which is the intensity of the spatial process. And then the symbols here, both red and blue, are the actual statistic at that particular scale of the O-ring statistic itself. And actually, we could see here that the statistic is actually much, much higher than the lambda itself here, up to a distance of about 1,000 kilometers. And that was very clear as well when you look at the data of 2009, where up to 1,000 kilometers, the observed value was actually higher than the intensity of the spatial process, which indicated to us that the distance to which inoculum was being contributed from one source to another to cause disease was about 1,000 kilometers. And so what that does mean, therefore, 1,000 kilometers is actually a distance, is equal to the linear distance between Florida and Georgia, for example, South Carolina. And so we surmised that the inoculum sources that is coming from the south is probably causing the infection in the states of Georgia, South Carolina, or North Carolina. However, the infections that are occurring in the Great Lakes region, for example, are not likely to come from Florida, but they are likely to come from outbreaks that are very close to South Carolina or North Carolina, or some unknown sources within that particular region. And so we could actually tell, based on this particular information, we could tell our farmers or growers, for example, if you're in the northern part of the country and you have an outbreak, for example, say in Georgia, in North Carolina, we should probably be a little bit worried that with the time, you're probably going to see some infection taking place. But if you don't have anything in Georgia, South Carolina, and you are, say, for example, in Virginia, New York, and you only have infection occurring in Florida, you probably need not to worry about the disease. So this particular finding helped us better, inform our growers in terms of the timing and the sort of scouting of their fields to be able to see if they have symptoms and if they need to spray any fungicides at any given point in time. So this 1,000 kilometers is actually the extent to which the inoculum can move. If you have two sources, one field that's not infected and a field that is actually infected, the inoculum can spread up to 1,000 kilometers. And so we wanted to sort of look at this a little bit again, using an alternative approach, to be able to figure out if the numbers that we're coming up with based on the point pattern analysis actually indeed are correct. So to be able to do this, we went back and sort of looked at the aerobiological principles. And one of the things that I looked at was the finite leap model developed by Ayla in 2008, 2003 on aerobiology, looking at aerially dispersed pathogens and how how things like spore concentration, wind velocity affects spore transport. So this is the finite leap model developed by Ayla, the one with the D. For example, this is the probability. D here is the probability that spores can leap over distance X, which is actually indicated here. V, F, and Q, these are aspects related to the aerobiology of the pathogen, like inoculum production, the ability to survive and escape. Lambda is still the intensity of the spatial process, and G and B, these are aspects related to the wind mechanics in terms of how wind affects spore deposition. And if you look at the equation of D, you have lambda, which is what we're actually looking for. The change in X, which what we're looking for is actually both in the exponent and also is the multiplier of this particular equation. So you cannot really make X here a function of the equation. So one approach to do is actually to use a Lambert function to be able to do that, which is actually indicated in here. So once we are able to do to make X as a function of the equation itself, we were able now to sort of get some estimates. So we know that these are probabilities which can range from 0 to 1. But realistically, for aerial pathogen, D can either be either 0.01 or 0.1. So if you take D 0.01 and plug it in this particular equation here, you get about 820 kilometers. And if you take D equals to 0.1, you get about 1150 kilometers. And so, and we can see actually that these values are very, very comparable to the 1,000-kilometer range that we got from the spatial, from the point pattern analysis. And because of that, it gave us quite a lot of confidence that sort of, we can actually confidently say that the farthest the inoculum can move, and cause disease from a particular source was about 1,000 kilometers. So that was very humbling and sort of comforting as well. So, all right, so I'm going to change gears a little bit and sort of talk about the risk of disease outbreak, after talking about the temporal spatial aspects of it. So one of the things that we know, we're dealing with a very large area in the eastern part of the country. And one of the things that, growers are always interested in is, okay, what's the risk of disease showing up in my state? When should I worry about the disease? And when do I need to spray? So we wanted to sort of provide some information so that growers can have an idea, or we can have an idea ourselves, because we didn't know this in the first place, to really show, have some numbers in terms of how the risk looks like during the growing season. So to be able to do this, we resorted to sort of looking at the, the hierarchical Bayesian models that combine survival analysis, spatial pattern analysis, as well as Bayesian approaches, to be able to figure out the process itself. So this is just the model that we implemented to be able to get these numbers. It has 3 parts to it. We have the data model, which basically describes the distribution of the data of interest to you, conditional to a particular process, and the parameter that you choose for that particular model. So in this particular data model, we're just looking at a very simple weighable model for survival analysis, and it has components to it. We have the beta, which is the coefficient. We have xi, x is actually the covariance, and wi, these are actually the random effects of interest. These random effects are actually summarized at the state level. And the process model basically describes the description of the unknown random effects, at the state level. And we are actually assumed that they follow a conditional autoregressive model in our particular case. That's the one that we choose to describe our data. Of course, lambda is still the intensity of the spatial process. The parameter model basically is just an indication of the prior distributions in Bayesian analysis as the priors. So we define priors for beta, lambda, as well as the survival function as well. Okay. So this model was implemented in Winbugs, and then of course the data that we utilized came from the disease monitoring network. And so we had three different models that we looked at. We just looked at this standard survival model that has no random effects, and then a survival model that has a structured effect, and then of course one that has unstructured random effects. And then without going into a lot of what was done, we just used the DICs and the change in DICs to be able to identify the model that worked best. And based on the numbers that we had, the random effects model with the structured random effects was actually most appropriate for the description of our data. So just looking at some of the results, just looking at the risk of disease outbreak, 2008 and 2009. On the x-axis here, you have the days after the first outbreak, which normally typically occurs down in Florida. On the y-axis, you have the risk. It changed. For example, in 2008, it was high on cucumber compared to squash or other cucurbits. But in 2009, it was higher in squash compared to other cucurbits. And just shows this figure just illustrates the dynamic, the differences. Because a lot of this, for those of you that are more familiar with the Downy mildew has what it calls some host specialization. And actually it focuses, the pathogen and the host, they really interact in a different way and in different strains. And this is very typical. If you do this over the years, you'll actually see changes in terms of the risk of disease. So, but if you look at the standard, survival approach, is just looking at the time for disease outbreak. We did this for 2008 and 2009. And just if you look at the distribution of the time of disease outbreak, the shorter it is, the higher the risk of disease onset compared to when the time to disease outbreak is actually much longer. It was very variable depending on where you are. For example, in Florida, had the lowest time. It had the lowest time to disease onset, which is not very surprising because it's very closer to the source. And other states like in Maryland took a little bit of time before disease could actually show up there. And we had a lot of variability from year to year. And I said a lot of that has to do with the ability of the pathogen to survive during transport. The hosts that are actually being infected that are actually out there, and of course the environmental factors as well. So we use the Bayesian model to be able now to plot actually the risks themselves, because this is actually what we are much more concerned about. And this is the map of the risk of disease outbreak in specific states. For example, we find that the more red it is, the more positive values you have, the higher the risk of disease outbreak. And the more negative values or more blue it becomes, the lower the risk of disease outbreak. And so we can see here, for example, Georgia, North Carolina, Virginia, and some states in New York had very high levels of disease compared to Texas, for example, in 2008. In 2009, Texas, very low levels. Florida, somewhere in the middle. North Carolina, still high levels of disease. Pennsylvania, also there are higher levels of disease. So a little bit of variation in terms of disease. But what we can actually see, we have this group of states along the mid-Atlantic region that's always somehow have higher levels of disease. So just to summarize, therefore, we have just high risk of disease in North Carolina and Virginia in both years. There's a cluster of lower levels of disease risk around the Great Lakes region over here. And then a cluster of low levels of disease in southern states, Texas, Mississippi, Alabama, as well as Louisiana. And so for the first time, we were able to actually put some numbers, level of risk of disease outbreak in some of these particular states. So one of the things we wanted to see is whether how well the Bayesian, just look at some comparative differences between the two models. For example, the standard approach vis-a-vis the Bayesian model that we actually utilized. So just put some numbers here. The DIC for the standard approach was 2,428. The DIC for the Bayesian approach is 2,410. So there's actually the change in the DIC by using the BIC was about 18 points, which is actually much more, which indicates a very significant change. And if you look at the numbers, for example, there's a little bit of a difference. If you look, for example, Texas, if you just take the standard approach of survival analysis, you find Texas over here, the risk of disease somewhere in the middle. But here, if you take the Bayesian approach, it actually has the lowest in terms of disease outbreak. And so if you look at other states like Wisconsin, it has the time to disease outbreak is actually much longer, of course, and the corresponding one here, for example, is also a little bit longer. So there's some correspondence in between, but overall, they are not falling, they don't go hand in hand pretty much. And a lot of that is because the Bayesian approach accounts for uncertainty in terms of the parameters of interest that we're having. It's taking into consideration also the spatial autocorrelation between the observations that you have, because observations that are very close to each other are going to be very similar compared to the ones actually further away. So, and that gives us a better framework to be able to meaningfully estimate the risk associated to disease with the disease outbreak. All right, so I'm going to go to the third component of my talk, and one of this element just focuses on epidemic expansion in time and space. And for those of you that are familiar with the literature, this can actually, the epidemic expansion in time and space can be represented by this equation here. And the variables here actually defined as indicated here. But what my emphasis here is actually on this particular component of the model that actually, of the function that I'm actually interested in. This component here is actually known as the contact distribution. Yeah. So the contact distribution just refers to the probability of inoculum moving from one particular location to be able to cause disease at some distance away from the source. Yeah. Why is this important? For aerially dispersed pathogen, which is the focus of my talk today, this contact distribution has what we call a power law tails, and because of that, it results into epidemics. Aerially dispersed pathogen results into epidemics that have dispersive characteristics with a sort of accelerating velocity. Okay, and so they don't have a constant velocity. The velocity is actually accelerating in the distance, and so for aerially dispersed pathogen, this contact distribution is actually proportional to 1/s, which is the distance relates to this parameter called B. And this is the parameter that I'm actually interested in. So the B parameter is actually the steepness of the disease gradient. Of course, the shallower it is, the inoculum is not going to go very far. The epidemic front is not going to go very far. But the less shallow it is, then of course, the epidemic is going to go over a longer distance. So why is this parameter, why was it of interest to me? One of the things that we looked at, when we look at the literature out there, so the paper published by Chris Mant at Oregon State with his colleagues in 2009, when I looked at these epidemics of plants as well as animals, for example, data-led by stem rust, southern corn leaf blight, West Nile virus, and the avian flu, you could actually see that the parameter, that spread parameter, was fairly consistent in terms of the numbers, around a value of about 1.9, regardless on how it was actually estimated, whether it's temporal or on a spatial scale. But I was a little bit intrigued because it sounded as perhaps some fundamental mechanism related to that. But one thing we noticed clearly, of course, this particular epidemics were only done once. And so we are just a little bit curious whether if we did this over several epidemics, whether we could still find a very stable value of B. And so we went back to our data set out of the monitoring unit. We did have a lot of data from 2008 to 2014, looked at all these particular epidemics and tried to figure out, okay, how can we generate some of these numbers and see how well the values look like. So we estimated B based on the data set that we generated, and this was just estimated using either the temporal regression, very simple equation here, and then the spatial regression, just taking the velocity of spread, where S is the distance, B is the parameter of spread. If you do the regression, you get the slope. The slope, for example, B, the inverse of that will give you the parameter of B itself. So we did that. So this is some of the data that we generated for 2008 to 2009. On the x-axis, you have the date. Then on the y-axis, this epidemic extent. In other words, the area that was covered by the wave front during that particular season. You see there was a lot of variability. For example, the highest area was in 2009, okay? And the lowest area was in 2012. And there was a lot in between. So this heterogeneity in the data set, gave us a lot of confidence to be able to see, okay, how meaningful or how reproducible the value, the parameter B can actually be. So if you look at the value of B itself, so after looking at the temporal and spatial, we fit it on a regression, the temporal spatial model, and then we looked at, of course, how well the model did. We look at the coefficient of variability, R squares range from 0.61 at least 0.97 for the temporal regression model. So the fit was not always very good in all the years, for example. We look at on the spatial component, range from 0.59 all the way to 0.98. So there's a little bit of variability in terms of the fit of the model itself. But if you look at the values of B, those range quite a lot from 1.77 all the way to 3.5 if you look at the temporal, and then from 1.51 all the way to 3 up to 4.16. So there's a very big range in terms of the parameter itself. So almost like double, from 2 all the way to 4. So we actually did some very simple analysis to see if there was some consistency, in terms of the parameter itself. Just very simple analysis of variance, where we did all the data of the years and look at the interaction between the year and the time. If there's any interaction between year and time or year and distance, then it would actually tell you that particular parameter is actually probably not stable. It's changing depending on the year of interest. So we eliminated the bad years where the regression didn't work very well. We still found a very significant interaction, particularly for the temporal, and a very marginal, non-significant value, for the spatial regression. And basically, we could actually conclude very well here that it's very, 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 very likely, that this particular value of B equals to 2, as has been in the literature, is probably likely to be different. So if you do have several realizations of the epidemic, most likely that value is actually going to be different from 2 itself. Now I'm going to explain a little bit about the implication of that later on in my talk. All right, so I'm going to come to towards the end of my talk today, and so one of the things that I'm going to be talking about is on monitoring of the epidemic. This work was done in collaboration with Dr. Alan Lloyd in the Mother Department, and Morik was our student was actually in the biomath program. And one of the things that I was interested in that Morik did was try to figure out how can we utilize the information that we have based on the sentinel plots for monitoring disease to be able to help better use our resources that we have. We know disease monitoring is very, very expensive. You need the resources to be able to do that very well. And we have a very large area where our network for monitoring is actually based. So what we wanted Morik to do was to be able to figure out, okay, based on the data set that we have and the reports that we were generated, can we look at the network analysis of the data and trying to figure out whether we can sort of identify some areas of interest that could be targeted for monitoring and if needed for treatment if you have to reduce the inoculum. It's very, very important that I emphasize that this data set has been analyzed based on what was actually reported. So anything that was not reported was not really included in this network analysis. So what Morik did was simply looked at static networks, based on the records from 2008 to 2016. And we looked at the distance between any particular node, calculating that distance based on the power law dispersal canal that I just showed in a few slides back, and then grabbed the adjacency matrix, based on these restrictions here. She also went ahead and looked at the dynamics part, the dynamics network as well, which just involved completing the static network, of course, and calculating the link weights every week. So the link weight is actually given by this particular equation here. If you look at this part, is similar to the static part of the static network here, and then this is actually the dynamic component of it, which includes the wind that's actually responsible for the movement of the pathogen during the season. And the probability that a particular node in any given time got infected is actually given by this particular equation here, where this one in red here is the probability that that particular node was not infected in the previous time step here, whereas theta here represents the probability that that particular node was not infected by the neighbors around it. Okay, so that's basically, in simplicity, what we did, or what Morik did. So I'm not going to go to the details. I'm just going to show you some of the networks that Maurik generated, from week 10, which is about March, all the way to week 2025. This is the dynamic network. The thicker the lines are, the higher the probability. It's indicated here by these symbols here. If you look at, for example, 2008, most of the infection, as we can see, started from Florida, which pretty much because of the wintering. And you can actually see this higher probability here between nodes, but there's nothing really happening in the rest part of the country at that particular time. But with the time, you find there's actually a higher probability of nodes getting infected as you advance in time. And then by the time you reach at May, sometime in May, for example, you have quite a lot of points that have a higher level of infection, particularly along the mid-Atlantic region. So there's a little bit of variability. For example, in 2008, 2014, there's very little happening compared to, say, 2015, where the probability was much higher. So this particular data set, where you have on the x-axis the latitude, longitude, and latitude, help us better visualize, how the network of Downy mildew looks like and how it's actually changing both in time and space. And as I said before, epidemics are evolving from year to year, and we have differences in terms of the pathogen, the environment, the hosts that are actually being planted, and of course, the wind is actually moving the inoculum back and forth is also very different. So invariably, you're going to have different networks over time as you realize different epidemics from, say, 2008 all the way to 2015. So I said, okay, one of the things that we were interested in, is to sort of to see among some of these nodes, which of these nodes are very, very important. And as I said before, the reason why we're doing this is because we know the monitoring is very, very expensive. And because it's expensive, we want to tailor specific areas, that we could actually utilize for monitoring. And if needed, we can actually utilize them sort of to control the disease, to sort of slow down the epidemic progress. So what Maurik did, basically, she actually looked at different measures, centrality measures, and utilized those ones to be able to identify the most important nodes. Okay. And after doing that, we actually simply removed those nodes from the network and actually see to what extent that affected the progress of the epidemic in time and space. This is some of the data that Maurik got. So we have the prediction here is the prediction of probability of infection based on all the points that are present in that particular network. For example, in 2008, blue is red, the probability is very low, high. Red is probably very, very high. Okay. And if you look at the betweenness, degree, and the eigenvector, these are some of the centrality measures that were utilized to identify the nodes of importance. And the nodes of importance, I apologize, it's a little bit small to see. The nodes of importance are actually diamond shaped actually in here, for example. And so what she did was take those ones out. The goal here is that if the centrality measures identify nodes that are actually important, if you remove them from the network, then it is actually should prevent the propagation of the epidemic northward, for example. And so when you look at the betweenness, when she removed the nodes that are actually identified to be important in terms of betweenness, pretty much the epidemic did not propagate itself towards the north. But if the nodes were removed using degree and the eigenvector, for example, the final epidemic extent of the nodes are actually, probability of infection was actually very similar when all the nodes were actually present within the network. And so the betweenness measure was actually very, for this particular data set, based on what was observed and what was present, was actually a very good centrality measure to be able to identify the nodes that were probably important in terms of the epidemic progress. And then, of course, for those of you that are more familiar with network analysis, the betweenness measure basically indicates that a node that is actually central, that node can act as a bridge. And if you remove that node from the network, it's probably going to contain the movement of the epidemic. On the other hand, if you have something like a degree, a node that's actually identified by the degree measure basically indicates that that node is actually connected to many other nodes. and and if it's important, it can be a kind of like a super spreader. And so, depending on the measure of the centrality that is actually more appropriate, it has a very important element related to epidemiology and spread of the pathogen. So, in summary, therefore, the highly connected nodes were actually observed in Maryland, Michigan, North Carolina, Ohio, South Carolina, and Virginia. And for the first time, we were able to identify some of these particular nodes, and we could actually tell our collaborators that are scouting to focus on some of these particular areas. For the system that we have right now, we don't spray, because it's used for monitoring and reporting and forecasting. But if you were to contain the epidemic, one way would sort of to target some of these highly connected areas and to spread them to, if you were to reduce epidemic spread, particularly the ones that are actually located in North Carolina, because things are moving from the south to the north. All right, just to summarize, therefore, so if you look at the temporal spread, we are able to identify the spread new infections, for example, 1 to 2 cases occurring per day, and we will notice that the rates are much higher in northern states compared to southern states, primarily because of the shorter duration of the epidemic. But because everything is starting from the south, the states in the north can afford to wait to do anything until they see something happen in the south. And so those growers that are in the north benefit quite a lot from the monitoring that is being done primarily in the south. And because of that, of course, they have the luxury to wait and see what's happening in southern states like Florida, Georgia, South Carolina, before they can actually do whatever they're doing, whatever they need to do in their states. And then as far as the spatial spread is concerned, the epidemic moves quite faster, about 10 kilometers every day. And what was important here is that the outbreaks in the northern states are not likely to come from Florida, but the ones that are in the mid, like South Carolina, Georgia, are most likely coming from overwintering sources from Florida. That's something that was very, very important to report out of this particular study. But if you look at the risk of spread at the landscape level, we actually see that the states in the mid-Atlantic region are always, at a higher risk of developing the disease. And this has some, implications in terms of monitoring. These are the states where we need to put more of our effort in terms of disease monitoring earlier on in the season. At the current state right now, in terms of the monitoring is concerned, it's really not real time, and there's still some challenges because we're dealing with a very large area. There are some challenges in terms of where the nodes need to be, scouted, where they need to be reported. And some of this analysis has helped us better sort of tailor some of our efforts to where we really need to put our resources in terms of monitoring and reporting. And then as far as the power law is concerned, as I indicated before, the B parameter, people have always looked at it as a value of B to be representative of the steepness of the disease gradient for aerially dispersed pathogen. But that has been primarily because they have looked at only one scenario or realization of the epidemic. But if you look at different scenarios of realization of the epidemic, most likely that value is not going to be very appropriate. And my opinion is that this particular value is that the B value is going to be situation dependent. And if you use a value of B, that should be considered as the lower limit of the spread parameter. And factors like atmospheric spread, atmospheric condition, environment, all these factors are going to influence B. Because if you incorrectly use B equals to 2, for example, that value will tell you where the epidemic front is likely to reach. But if it's actually probably more than 2, of course, it has some policy implication in terms of disease management. And finally, based on the network analysis, we were able to identify areas that are more important for us in terms of monitoring, and we're actually able to show that the removal of some of these sites can reduce epidemic spread. And these sites can actually be targeted for early surveillance of the disease. And it's very, very important to notice here that this inference is actually based on what was reported. Anything that was not reported that is not part of this particular network, was not taken into consideration. And so that's a caveat that we should remember. At least everyone should remember when you're actually interpreting some of these results. Okay. All right. I just want to take this opportunity just to thank everybody who has helped me do this work. A lot of work, over the years. We have Mauric, my graduate student, with Alan Lloyd, of course, and we have Lucky also to help with some of the modeling work, my collaborators, and then of course, member of the CDM IPM type team in terms of reporting, collecting all the data that has made this work possible to report in this particular format. And with that, I'll be more than happy to answer any questions that you might have. Thank you. Yeah, thanks, Ralph. So do we have any question, John?
Well, everyone, feel free to unmute yourselves and ask a question or put a question in the chat for Peter.
Hey, Dominic, go ahead.
Hey, Peter, I thought that was really interesting, that work you did on the B value. But I wonder why anyone would even think that it would be consistent, like from year to year. I mean, like environment is so different. So,
Right.
I mean, I just want to hear your thoughts on that.
I mean, I think one of the reasons why this was brought up is because they are, I've attended meetings whereby they said that you can just use the B value equals to 2 to get kind of like a baseline of what you would expect, and so, but that prompted me to say, okay, why should just use P equals to 2? Why do you think it's supposed to be 2? And that's why I went back and sort of looked at this, because we know if it's not 2, that area is going to be dependent upon that particular value. And so if you use a very long value of 2, then of course you're going to get a very different value altogether in terms of policy, in terms of where the epidemic is going to likely to be. And I think, to me, I think the reason why people like using 2 is because it's very easy to do, and it can give you a very quick answer to what you're trying to. So you can tell people what you expect, but they might not have the same data set that we have to be able to do some of these things that we are able to do. And that's probably my take on that. Yeah. Ralph.
Yeah, cool stuff. I have a question about the connected nodes.
Go ahead.
You can hear me okay?
Yeah, go ahead. I can hear you.
So you're showing these connected nodes in different locations in different states. Mm-hmm. How confident are you in these nodes? I mean, unfortunately, I couldn't kind of see all the detail on the individual maps. I mean, so are you saying that there's one location in North Carolina or Maryland that?
Oh yeah, no.
Or is it the whole state?
Not the whole state. We have individual coordinates for those particular points, and so
yeah, but
we have.
Right, but you believe that those particular focal points are where the pathogen is funneling through before it migrates, say, up north? Is that your suggestion?
What you are suggesting is that those particular nodes, if you look at just betweenness, as I explained before, these nodes sort of they operate like kind of like a bridge, so to speak.
Right.
We call them high traffic nodes. So basically, this is areas whereby, for one reason or the other, the pathogen is being, they actually use it like kind of like a metapopulation, hopping points, where the pathogen can easily hop from one particular site to another one.
I follow, and it's really intriguing. So you're saying it's like a super highway for the pathogen? It's that specific, or is it just? I mean, how broad is this highway?
I mean, well, that is the terminology that we use in network in epidemiology when you're describing the nodes themselves. They're kind of like high traffic nodes where basically you have a lot of movement, where the pathogen, the spores or movement is like to be. They can be a very good source of the inoculum to other particular locations in that particular area. Pretty much, that is the interpretation of that. Yeah.
Cool. Thank you.
And then maybe I didn't answer another how confident we are. I didn't show some of the data. We have some information about the errors of the model when we took out those individual values, those nodes that were presumably important. The errors that came out of actually went up, indicating how important they are in terms of the prediction. Yeah, I didn't show that because of time. So.
Great talk, Peter. Quick question related to why you see spread kind of up the East Coast versus kind of to the West. Is that primarily driven by wind patterns, do you think? Or is there another environmental variable that could be driving that?
Yeah, I think there might be a couple of things, because typically, within that particular corridor, for example, if you look at the West Coast, we only have Downy mildew in California, and in between there, Utah, Oklahoma, we have very little happening in there. And my feeling over the years has been the heterogeneity. The environment is more conducive in the eastern part of the country. As you move west, the environment becomes less and less conducive. And of course, there's also heterogeneity in terms of how well the pathogen can actually survive in there as well. And because if the environment is not conducive, the pathogen is probably not going to survive that much. But also that we should also not forget the fact that perhaps there might be also just not so much production of cantaloupes or cucurbits in that particular region as well. So it's a combination of so many factors. John, yeah. Oh, Chris, yeah, that was Chris, yes. Did I answer your question, Chris?
Yeah, that was another question I had, was the production levels in different states, and how much that varies over the years.
Yeah.
Anyone else have any questions to ask or put into the chat? We have a few more minutes. Okay, well, thank you so much, Peter. That was a wonderful talk. And thank you also, Anders, for the introduction. Really appreciate it.
Thank you, John. It was my pleasure.
And I posted in the chat window, there's a virtual social hour starting immediately following the forum. The link is there, and this was recorded, and we'll post the video to our YouTube channel as soon as possible, the Center's YouTube channel. So thanks everyone for joining today. Really appreciate it.
Okay, thanks, John.
Thank you.
I'm going to stop sharing.
Okay.
If I can remember how to do that. Okay, so pause, stop. Okay, good. So unfortunately, John, I'm in the office, as you can see, so I'm just on my way home. So I'm probably not gonna show up for the social.
Oh, no worries, no worries. Thank you so much. You take care.
Okay, bye-bye.
Bye.